Alright, so this is the last lecture in Chapter 8. I'm recording it because I have to be on travel. So I'm just recording it in my office. We covered a lot of material, a lot of the hydrodynamics, the fluid flow, then we added the thermal. We had the energy balance, and remember, you keep going back and forth between the rate balance and the energy balance. We focused on laminar flow in circular tubes. We got some good results, especially for the Nusselt number is a constant, 4.36 and 3.66 depending on what's happening at the wall. If Q double prime at the wall is a constant, then you get a constant Nusselt number 4.36, and if the wall temperature is a constant, you get a fully developed laminar flow. The Nusselt number is 3.66. Both of those use the diameter d for the length scale in the definition of the Nusselt number. Then we moved to convection correlations. That was the convection correlations for laminar flow. If you have turbulent flow, the big one is the Didas-Boelter. So it's 0.023 times the Reynolds number to 0.8, and then the Prandtl number to an exponent n. N is equal to 0.4 if it's being heated, and n is equal to 0.3 if it's being cooled. That gives you the Nusselt number. As long as you're greater than 2300 Reynolds number, then you're expected to be turbulent, and as long as your length is greater than about 10 diameters, then you're not in any entrance region. You're in the fully developed turbulent regime. If you have a non-circular tube, then what you need to do is use the hydraulic diameter, and then go ahead and use the turbulent correlations. The textbook also has a number of laminar flow with the constant. You just change these constants if it's a laminar flow in a rectangular duct or a triangular duct, and those are in tables. But if you have a non-circular tube and it's turbulent, use the hydraulic diameter. Okay, I'm not really covering concentric tubes, really not covering heat transfer enhancements. It's important, we just don't have time. And we're not covering flow in very small channels, microchannels. Today I have covered all the material that we need to cover. I just really need to solve some problems. Well, let's take a look at this problem. So we have a solid copper cold plate, that's the name of it, used in electronics for cooling. Heat dissipating electronics are mounted on the top and the bottom surfaces. So up in here you have some heat that's being dissipated on the top as well as on the bottom of that cold plate. And water flows in rectangular channels. So the water is flowing here and here and here and here, etc. The cold plate has a dimension of cap H of 10 millimeters, so over here 10 millimeter, and cap W, which is 100 millimeter, cap W 100 millimeter, and lowercase h, lowercase w is 6 millimeters. So this is 6 millimeter, which is the height of that square channel, and W is the width of that square channel. Both of those are 6 millimeters. And delta, this is 4 millimeter. So that's the webbing thickness between the channels. And water enters at a given temperature Tmi. The mean temperature coming in is 300 Kelvin and has a velocity of 1.1 meters per second. That's the mean velocity. I forgot to point out one thing. If you do the math, you can see that the thickness of this part on the top is 2 millimeter, and the thickness down here is 2 millimeter, and likewise the thickness on this very edge over here is 2 millimeters. All right. But the web in between is 4 millimeter. Okay. The top and the bottom plates, because of the electronics that are mounted on them, is approximated to have a constant surface temperature of 360. So this temperature of the top plate as well as the bottom is 360 Kelvin. Assume fully developed flow for the water in the square channels and calculate the outlet water temperature. So over here, we're coming out with the temperature of the water, the mean temperature exiting. That's what they want to calculate, coming out. And the total rate of heat removal from the plate. That total rate of heat removal will be from both the top and the bottom. Use the following properties for copper. So the conductivity is given, and for water, the density is given, the specific heat, viscosity, thermal conductivity, and Prandtl number all given, so that avoids having to jump into the tables and evaluate properties. Well, there's a couple ways of solving this problem. Probably the easiest is to go ahead and exploit symmetry, but not really the smallest symmetry section. But if I cut this webbing right here down the middle and I just go that way, what I do is I have a square channel for the water to flow, and then I have copper surrounding it like that. And the top surface of this copper right here, I'm not trying to change color now, is at TS, and the bottom surface is at TS. And this runs all the way down. I'm trying to show it in the third dimension, and the flow comes in here. Well, how does the heat transfer into that water? Well, you would say that it transfers directly across this copper section, but it can also travel up in that webbing and then into the fluid. So it can come up on the sides and into the fluid. Well, what we see is the bottom acts like a plate offers some conduction resistance, but that the top parts, the sides, act as fins. So maybe I cut it because of symmetry again, and notice that it's coming from both the top and the bottom. So now what I'm going to do is I'm going to say I have half a channel, okay, and let me try and draw this. That's that symmetry right there. So that's acting as insulated, and this is cut half of that web. That's acting as insulated. The top acts as insulated, and the bottom. So what do we have? We have everywhere along this bottom surface is TS. We have another temperature, I don't know, call it TB or something, and it's everywhere along this channel right in here, but as it goes out along that edge, which acts like a fin, it drops, and so you'll get a lower temperature. Well, I would assume that TB is the same going all the way across right here, and what you can do is you can model it like this, even put those two halves together, and what you'll have is how's that? A fin that's insulated, and it has a thickness delta equal to, well, the thickness, the T, let me do that. That's our traditional symbol for thickness. T is equal to delta equal to 4 millimeters. Okay, and then we have convection or heat transfer coming up and going out that way, as well as that way, conduction and convection off of that fin. So let me try and, I know I'm jumping around here for different sections, but this would be, some of the fluid would be flowing in that section, some in that section. If you look at it, it's the same as here in the bottom half. And then we have conduction here, and uniform temperature at the bottom, TS of 360, and then a uniform base temperature, and then that fin. Okay, so what do? Is we say, we're going to have we're going to basically go back and use our fin analysis techniques to help us solve this problem. So what I need to get is I need to first of all get the convection coefficient for the water flowing in the square channel. In order to get that, I need to get the Nusselt number. In order to get the Nusselt number, I need to get the Reynolds number. In order to get the Reynolds number, I need a hydraulic diameter. So let's go ahead and calculate a hydraulic diameter for this problem. So the hydraulic diameter is 4 times the cross-sectional area divided by the wetted perimeter. What I would do is take a look at 4 times the cross-sectional area. I'll just look at one of those channels, and so it has an H times a W will be the cross-sectional area. They're both the same. H and W are both 6 millimeters. And then the wetted perimeter would be 2 times H plus W. All right. So when we throw our numbers in there, we get that the hydraulic diameter is 0.006 meters or 6 millimeters. We go to the Reynolds number, rho U mean d sub h divided by mu. So we have all that information. The density is given, the velocity is given, 1.1 meter per second. I calculated a Reynolds number that's 8.10 times 10 to the 3. So it's over 2,000-ish. So it's turbulent. So we're going to go and get a Nusselt correlation. We'll use the Dietz-Boelter, 0.023. Reynolds to the 0.8. Prandtl, because the water is being heated, it'll be a 0.4. Okay. When we calculate the Nusselt number, it comes in right at 61.0. I also went and calculated it using, I usually subscript something like this, Nusselt, Dietz-Boelter, and then if I want, I'll compute Nusselt number and that other correlation. What is it? I'm going to mispronounce his name, Gronelski's correlation. And when you calculate that, it comes in at 59.7. There's not much of a difference. These are basically the same numbers. So the two methods give the same Nusselt number. So we can unravel the Nusselt number to get the H. The H is Nusselt times the thermal conductivity of the water divided by the hydraulic diameter. And when we get the H, it comes in right at 6,135 watts per meter squared degree C. Well, that's pretty much the contribution from Chapter 8. But now what we need to do is fit it in to the analysis and make the calculation as needed to find that outlet water temperature. But that's a big part of this problem, getting that convection coefficient. Okay. So now what I want to do is go back and take a look at our fin equation. So what is our fin thickness? Our fin thickness, I already mentioned, is 4 millimeters. So if I put T over here, it's 0.004 meters. And I want to calculate the fin length, L. We don't need to correct it because it's insulated at the tip because of symmetry. And so that L for the fin length is half of H. So it's 0.003 meters or 3 millimeters. The fin parameter M is the square root of 2H divided by KT. That's for a rectangular fin of thickness T, and we're basically neglecting the edges, which are really way over here. It's like this edge and that edge. Okay, but it's basically the length which cancels in the ratio. But it's 2H divided by KT, the square root of that. When we calculate it for this fin, the fin parameter comes in at 88.5 inverse meter. All right. Now, the product ML is usually computed, and then we take a look at it. The ML is 0.2656, and it's dimensionless. If you want the efficiency of the fin efficiency, for the single fin, it's the hyperbolic tangent of ML divided by ML, and that gives us an efficiency of a whopping 97.7%. It's as if that fin is isothermal. There's a small temperature variation throughout the fin. What we want to do is we want to compute an overall efficiency for convection off of both the unfinned base part, if I can emphasize it like this, that's kind of an unfinned base part, with the finned part right there. And I'm just showing you half of it there. But the equation covered, I think, in chapter 3 for that is that it's equal to 1 minus the area of the fin divided by the area total. The total area is the fin plus the exposed base times 1 minus the efficiency of one fin. All right, so what is this? Area of the fin divided by the area total. Well, if I look at it, you can maybe see it from this illustration. The area base is going to be the width W. So the area of the unexposed, the unfinned, will be B times the length. Using a different length, I better use W here. W is the length that you go down the channel, and the area of the fin for that one passage is going to be 2 times L times W. So when we add them together, the area of the fin is 2LW. You divide by BW plus 2LW. The W's cancel, and we're left with 2L divided by B plus 2L. And so that computes to a half, 0.5. So when we stick that into our equation to get the overall efficiency for the surface, it comes in even higher. It comes in at 98.9%. You could round that off to 100% and do just the same, but I'm trying to show you all the details if you want to reproduce it. All right, looks like I'm going to have to go to another page to finish this problem out. I hate to do that. Maybe I'll just try and scroll down. Ugh, let's try that. All right. So you have a resistance conceptually to go from TS to TB, and then a resistance to go from TB into the fluid in the channel. And this is, I know it's changing as we go down the length, but that resistance here is 1 over the overall efficiency of that surface times the convection coefficient times the area of that the fluid sees in the channel. Okay, and this is just a thickness of the copper. That I used that symbol already. That thickness, if I look at my illustration, is going to be delta over 2. It's 2 millimeters. Boy, I really don't. I'm trying to find other symbols here. Let's call it delta of the bottom, which is 2 millimeters, divided by thermal conductivity of the copper, Cu, and we have an area. Well, that area is going to be this distance right here. Okay. Well, what is that distance? That's 10 millimeters in this problem. It's, let me see what symbol they use in here. It's essentially S, which is H plus the 2 and the 2. It gives me my 10 high and 10 wide. So let me scroll down again. So this is cap S. We'll use that symbol. So these two resistances are in series, and so we can sum them to get the total resistance. So the total resistance, thermal resistance, moving from this surface, which is 300 and what is it, 60, to some mean fluid temperature, is going to be 1 over UA, if you want to write it that way, overall heat transfer coefficient times area, plus 0.002 2 meters for that thickness, divided by the copper conductivity 400 watts per meter Kelvin, times S. S is 10 millimeters, or 0.010 meter. We add to that 1 over the overall efficiency 0.989 times the convection coefficient 6,135 watts per meter squared degree C or Kelvin, doesn't matter, there's a delta T. And then we have the area for that, and the area is going to be, if you're doing it for a half channel, what is that area? It's going to be, this is a W plus 2 times half H, or so it'll be 6 and 6, it'll be 12 millimeters, 0.012 meters. All right, so when we calculate these, we'll get that the resistance conduction is a all right, so this number gives us 0.0005 degrees C per watt, and this one gives us 0.01345 degrees C per watt. And then I just detected a little problem. This H right here came from using the Nusselt number from the second correlation, but I calculated it, but I didn't want to use it. What I did was I calculated it from the Dietz-Boelter, which is 6270 watts per meter squared degree C. Not much different, but when I come over here, I actually substituted and used 6270, which gives me this number. Okay, so we add those up to get the overall resistance, 0.01345 degrees C per watt. And then what I like to do is go back and compare, and I say, well, what was the resistance due to that conduction through that copper slab at the bottom? That is a whopping 3.6%, not completely negligible, but the vast majority of the resistance is the 96.4%. It's really not just moving through the copper, but really it's the convection off. Because if this is 100%, you can't get a better fin, and that's pretty close to 100% for a fin surface. So it really is 96% is the convection, getting it off of the copper surface and into the fluid. But this is what we really need. We need that resistance. So the resistance is 1 over UA. Okay, I need to scroll down to get some more space. So if you think about the fluid going down the length of the channel, and the temperature here at the surface is a constant that was given to be 360 Kelvin. The temperature coming in of the fluid was 300 Kelvin, so that's TMI. That gives us a theta inlet. Mean theta inlet is 60 Kelvin. Well, what does the temperature do? Does it dramatically increase, or does it slowly increase? Well, for this problem, it's very, very, very modest increase in the temperature of the water. Oh, it's removing heat, but it's not increasing the temperature of the water much. And so theta of the difference on the exit is not that much less. I just know that because I made the calculation. But now let's make the calculation. What we do is we find that the theta on the exit is equal to theta on the inlet, e to the minus, and then you can put it as UA over m dot C sub P. That's this term, that UA term right there, and it goes in. Or you can express it as, instead of UA, you can put it as a reciprocal of R theta. The resistance. Anyway, so what I find is the exit theta divided by the inlet theta, the natural log of that is equal to, well, leave the natural log out, don't need to do that, e to the minus, and then we're going to have the mass flow rate. The mass flow rate, we calculated that somewhere. The mass flow rate down a half of the channel, 0.1972 kilograms per second. The specific heat, 4178 joules per kilogram degree C. And then UA, or the reciprocal of UA, is 0.01345 degrees C per watt. Just double check our units. So what's a joule per second? Isn't that a watt? A kilogram, kilogram, degree C, degree C. And when you make this computation, you get that it's 0.92. So theta on the exit is 92% of the theta on the inlet. The theta on the inlet was 60 Kelvin, the temperature difference. And so the theta on the outlet is 55 Kelvin. So the fluid temperature coming out, Tm on the exit, is 360 minus the 55. It comes out at 305 Kelvin. The temperature came in at 300 Kelvin. It goes out just 5 Kelvin higher. It comes out at 305 Kelvin. It doesn't appear to be a very efficient heat exchanger, but it is. It's a good cold plate. It could be better, as all things could be better, but it's still removing a lot of heat. Let's go back up and take a look at for part B. What is the total rate of heat removal from the plate? Well, there's a couple ways to calculate it, but since we know the inlet and the outlet temperature of the water, we can calculate it more readily that way. So let me try and fit it in by scooting up or scooting down. So we can calculate part B. The total rate of heat removal from the plate Q will be either the total mass flow rate flowing through all of those channels times the specific heat times the change in the mean temperature, exit minus inlet. And so we know this one, this is the 305, this is the 300, so there's an increase in 5 Kelvin. We know the specific heat is given right down here, right there, 4178 joules per kilogram Kelvin. It's just calculating that total mass flow rate. And that total mass flow rate, you just know the U, so it's going to be rho U sub m times the total cross-sectional area. For one channel, it's 6 millimeters by 6 millimeters, 0.006 times 0.006. That'll give me meters squared, but there's 10 of them, so that gives me the total mass flow rate. And then there you go. So rho U, blah, blah, blah. So when we calculate the total mass flow rate, I calculate it to be around 0.3944 kilograms per second. And then that gives us a total Q that's around 8,240 watts. All right, so let's take a look at this problem as well. We have air at 31 degrees C and a given volumetric flow rate entering a long plastic pipe that's smooth, that has a thermal conductivity of the plastic, has an inlet diameter and an outlet diameter. Not an inlet and outlet diameter, sorry, the inner diameter and outer diameter. And it has an inner diameter and an outer diameter for that plastic pipe. The plastic pipe is submerged in flowing water, and so on the outside of the pipe there's a large convection coefficient, and it's exposed to the water at 16 degrees C. The air is to be cooled from an inlet of 31 degrees C to an outlet of 21 degrees C. So there's a 10 degree C temperature change in that pipe. Determine the pipe length needed. So we want to find L. And then after we find L, we'll calculate part B. But what is that total pipe length needed? Well, what we're going to do is an overall energy balance, and we're going to say that the Q that comes into the fluid is going to affect the fluid, the air, by increasing its temperature. So Q is going to result in m dot C sub P, T mean exit minus T mean inlet. Okay, but how do I get that Q? Well, it's controlled by our convection heat transfer rate, our rate equation. So the rate of heat addition, Q, is equal to the H times the area. The area here is pi dL times an appropriate driving temperature that drives the flow. So wouldn't that be our delta T log mean? Sure, that would be our log mean temperature difference. So you put these two equations together, and what we have is we have that the length of the pipe, all right, I'm just going to try and skip some steps, is equal to m dot C sub P T exit minus temperature inlet divided by convection coefficient pi d. What did I write a pi p there? That's a pi dl, times delta T log mean. All right, let's try to start calculating some of these properties. First of all, I'm going to have to calculate the mass flow rate of the air. Well, we're given a volumetric flow rate. The volumetric flow rate, AV, is given right here at 0.07 meter cubed per second, but I need the density of the air. I look, it's not given to me anywhere in the problem statement, so I'm going to have to go and calculate that density. Well, what does it say about the pressure in the air? Have no assumption about that, so I assume 1 ATM. The pressure is equal to 1 ATM, all right, about 1 atmosphere. They give us the inlet temperature, 31 degrees C. You could go and you could calculate rho is equal to the pressure of the air, the molar mass of the air, the gas constant, and then that temperature. Let's calculate it on the inlet. So this pressure would be 101.3 kilopascal, 28.97 kilograms per kilomole, 8.314, depending on how you want to do it, kilojoules per kilogram or kilomole Kelvin. And then the temperature is 31, so 273 plus 31. So we calculate a density of 1.16 kilogram per cubic meter. You can put more digits on that, 1.161, etc. So if we calculate, then the mass flow rate is going to be the volumetric flow rate, 0.07 times that density. And so we get a mass flow rate 0.08128 kilograms per second. That's the mass flow rate. All right. So that one we can sort of put a check there. What about the specific heat constant pressure? Well, we would like to evaluate these properties at the mean or the average mean temperature. So 31 and 21, that's 52 divided by 2, what do you get? 26 degrees C. So the specific heat is around 1007 joules per kilogram degree C. The inlet temperature, the exit is 21. The inlet is 31. That's going to be a negative on that, so I probably need to switch it, put that negative out here, because it's being removed. The heat is being removed, or it'll become a negative delta T here. Let's do the H. Well, there's a lot of work. The pi and the d are known. Let's go ahead and calculate the delta T log mean. So the delta T log mean is the temperature difference between the 31 and the wall of the pipe. But it's not just that. We have to go through not only the inlet of the inner surface temperature of the pipe, we have to go to the outer surface temperature of the pipe, and then we have to go to the water temperature, which is our final fixed amount, which is the temperature of the water is 16 degrees C. All right, and so this is our mean temperature. So instead of calculating just an H here, we have to calculate basically a U, an overall heat transfer coefficient. That's the generalization of H. So we have 1 over the H on the inside, area on the inside, which is pi d inside length, plus, what do we have here? Through the wall of the pipe, natural log of d outer divided by d inner, divided by 2 pi thermal conductivity of that plastic pipe. Let's put case of P there, times L, plus 1 over the H outer pi d outer L. And the sum of those, if you just sum them up, you'll get 1 over UA. So UA, 1 over UA. Well, what I like to do is get rid of this L in each of these terms. So I'll put L over UA, and then I'll have 1 over H on the inside, pi d inside. So I have to do a little work on to get that H on the inside. And I'll have the natural log of d outer over d inner over 2 pi case of P of the pipe, and then 1 over H naught with outside pi d naught. So I just like to put check marks. Okay, I know this one, pi is easy, H naught is given, the thermal conductivity is given. I can calculate all these terms except for the H on the inside. So now we have to go and get that H on the inside. All right. The H on the inside, it's a standard pattern here, is I'll go ahead and I'll get a Nusselt number. From the Nusselt number, it's Nusselt K over D, but I got to get that Nusselt number. How do I get it? Well, I get the Reynolds number to see if it's laminar or turbulent flow, and then I check it. So what is my my Reynolds number? Well, it's 4 m dot divided by pi d mu. Okay, I'll get the mu viscosity. It's like 18.5 times 10 to the minus 6. So it's evaluated at that film temperature. Here, let's calculate the film, not the film temperature, the average mean temperature. So we need to calculate that viscosity at the average mean temperature, the mean average, which is 31 plus 21 divided by 2, that's 52, divided by 2, that's 26 degrees C, add 273, and you get 299, is 299 Kelvin, close enough to 300 Kelvin, so you get the viscosity of air at 300 Kelvin in the back of the book. You have the mass flow rate, and you calculate that the Reynolds number comes in at 3.74 times 10 to the 4th. It's turbulent. It's over 2300. You then use the Dietz-Boelter, which is, I get tired writing it, but 0.023 Reynolds to the 0.8 Prandtl. What's happening is the air being cooled or heated. It's being cooled, so it's 0.3. And that Nusselt number comes in at 94.4. So now we can get the H on the inside. The H on the inside is 16.5 watts per meter squared degree C. So we have now finally this H on the inside. So I calculate, there's a couple different ways of doing this at this point. This L, sometimes you can just pick and say, I'm going to do this for 1 meter. L is equal to 1 meter. If conceptually that works for you, you can go ahead and do that. You'll get a 1 over UA. What I found was that anyway I computed these, that when I went back and took a look, the resistance on the inside is about 56%. The resistance through the wall is around 43% of the overall resistance to heat transfer. And the convection on the outside is like 0.8%. It's less than 1%. It's almost completely negligible. It's the convection coefficient on the outside is so large that compared to the convection coefficient on the inside and the resistance due to the plastic, that it's a pretty hard to improve it. I mean, it's a very low resistance. Okay, so I have L divided by UA. When I sum that up, my numbers give me that L over UA is equal to 0.2297 with some extra change. All right. And so this is really L divided by some, let me leave it as U, but you can treat it as an H. Then you're going to have some pi dl, the L's cancel, and so you have this right here. This term replaces this term right here in our standard equation. So this is generalized to a U. That's generalized to a U. Pi d. Or you can say that that's equal to UA divided by L. Oh, all right. So the total length, let me try and fit it in right here. Did I calculate the log mean temperature difference? I don't think I did. Let's go ahead and calculate the log mean temperature difference. So it's going to be the difference between 31 and 16. So you'll put 31 minus 16. What is that for theta 1? All right, to calculate the log mean temperature difference, think about the theta on the inlet minus the theta on the exit divided by the natural log theta inlet over theta exit. All right, theta inlet, that'll be the 16 minus 31, which is negative 15 degrees C. Theta on the exit is going to be 16 minus 21, negative 5 degrees C. So the log mean temperature difference is negative 15 plus 5, that'll be negative 10, divided by 15 over 5, or natural log of 3. So the delta T log mean comes in (9.1) with a negative degrees C. All right, so I need to scroll down just a little bit. So what do we calculate? The length is equal to L over UA times mass flow rate, specific heat. The change in the temperature mean coming out was 21 minus 31 divided by the log mean temperature difference, negative 9.1 degrees C. Alright, so you can see how the negative signs take care of themselves. So it's 0.2297 mass flow rate. We calculate it to be 0.08128. Specific heat, look it up, 1007 times negative 10 divided by negative 9.1. And the length needs to be 20.7 meters. Alright, I need to scroll back up. And now that we know the length is that length, 20.7 meters, what is the minimum fan power to move the air through the pipe? Well, okay, this is fluid mechanics again. So we get the pressure loss is the friction factor times the length over diameter times 1/2 rho u mean squared. So the velocity pressure. We know the length, we know the inner diameter, we need to get that friction factor. That friction factor, you look it up as a function of Reynolds number off of the Moody diagram, or you can use the equation 0.79 natural log of the Reynolds number minus 1.64, all of that to the negative 2 power, and that friction factor comes in at 0.0224 using the equation, which agrees if you do it visually off of the Moody diagram. Okay, we calculate the pressure loss to be around 28.1 Pascal, newtons per meter squared. Now, if you want to know the minimum fan power to move the fluid, that would be W dot min would be the pressure loss. Would be the pressure loss times the volumetric flow rate. Well, we got the volumetric flow rate given in the problem statement, and so we can then just multiply those two, and you get that the fluid power is a 1.97 watts. W dot min. So that's the minimum fan power, assuming the fan is 100% efficient. Well, with that, I'm done. I just encourage you to again study the hydrodynamics, then look at the energy considerations, the thermal considerations, check, see if you have laminar or turbulent flow. If you have non-circular, check, use the hydraulic diameter. Forget these sections here, and I'll see you when I get back from my trip. Thanks.